Welcome back, guys. It's Mrs. Webb here. So today I'm coming to you to chat about solution stoichiometry. So this is the second time you guys have seen stoichiometry in the course, and really it's the same setup. The only difference being that we're adding a couple of different units to the unit analysis. Okay, so when we talk stoichiometry, we generally use this method in order to be able to figure out amounts, quantities of products or solutions. Remember, we can figure out which reactant will limit the reaction, all that kind of stuff. The big difference here is that we're going to talk about solutions, which means that we're going to introduce amount, concentration, and volume into our unit analysis. But otherwise, it's the exact same setup. Okay, so I've got an example here. Probably the easiest way to get into it is just to start looking at examples. And again, I want to really stress the importance of the setup. If you guys are able to set up the question, the unit analysis will come. It's really quite straightforward once you've got everything set up in the way that you have to answer it, right? So, and I know that I say it's straightforward, but it is challenging to do that. So the more you practice, the easier it will become. So here they're telling you we've got a solution of ammonia aqueous reacting with H3PO4 aqueous. It produces ammonium hydrogen phosphate fertilizer. And we want to know what volume of 14.8 molar ammonia solution is needed for the ammonia to completely react with 1.00 kiloliters of 12.9 molar H3PO4. Okay, so a couple of kind of keywords, right? What we're looking for is that we have a reaction. They're giving us, quantities for two parts of the reaction. They're asking us what volume of ammonia. Okay, so that's essentially your keywords to kind of tell you that this is going to be a solution stoichiometry or a stoichiometry problem. Even if you don't know what kind of problem, if you see that the question is giving you a chemical reaction, step one, regardless of where you're going, write that reaction down. So I generally do this as I read the question. We have a reaction between ammonia and phosphoric acid. So I write down my balanced chemical reaction. We have ammonia aqueous plus phosphoric acid aqueous. It produces ammonium hydrogen phosphate. Okay. And we balance our reaction. Make sure that it's balanced. Now, that's the first step. Even before I read the rest of the question, I write that down. And now I'm going to fill in the blanks as I'm reading. So they say, what volume of ammonia? First thing I write down is volume is my question mark underneath the ammonia solution. And right away they've told me that the concentration is 14.8 molar concentration, or 14.8 moles per liter. Remember that capital M unit refers to moles per liter as well. So I write that underneath the ammonia. 14.8 molar ammonia is needed for the ammonia to completely react with 1 kiloliter. Write that down. 1 kiloliter. I'm probably going to need it in liters, so I put it as 1 liter. And I know that because I'm dealing with moles per liter. And then they tell me 12.9 molar phosphoric acid. So I write that down. I write this down as I'm reading the question. Now I can visually see what the setup is. I've got information, quantitative information for one part of my reaction. I've got information for a second part, and they're asking me about some unknown on that second part. Okay, that right there indicates to me that I have to do some sort of a stoichiometric analysis. And remember that if I do that, I'm starting on the side with all of the information. I'm working to the side with the unknown, and the only way I can jump from the one side to the other is using that mole ratio. Now remember, that mole ratio and the setup is super important, because I know the last time that we did gas stoichiometry, a lot of students were really good with the analysis portion, But lots of students kept dropping this mole ratio part. So it's really important that you set it up the way I'm showing you so that you can visually see what's happening. And remember that in a unit analysis, we're going to start on the side that has everything. We're going to cross out all of the quantitative information to get moles of this known substance. We'll jump to the unknown substance using the mole ratio, and then we'll work through our quantitative data in order to arrive at the unknown unit. Okay, so the unit analysis. I started here with 12.9 molar, 12.9 moles per liter. So I'm going to put a check mark here because I've made use of that piece of quantitative data. I've got moles of, and I'm going to put H3PO4. Again, I highly recommend putting moles of what? So that when you get to that mole ratio step, you don't accidentally cross out the wrong mole with the wrong mole. Okay. Now, I have moles per liter. I need to get rid of this liters. So I look to see what information under all my known quantitative data has a liter in it. The only other piece is my volume. So I'm going to make use of that. In order to cancel out this liter that is underneath the division line, I need to have the liter from the volume on top of the division line. So I'm going to place it on top of this imaginary division line here. And liter will divide by liter, and it'll cancel out. So now I've used all of my information here on the known side, which means now I can jump to the unknown side using my mole ratio. So I'm going to cross that, check it off so that I know I've done it. My mole ratio is 2 moles of ammonia for every 1 mole of phosphoric acid. I need to cancel out mole of phosphoric acid, which means I need this mole from the ratio under the division line. If the phosphoric acid is underneath the division line here, and it's on top of the division line here, those two units will divide by each other and they'll cancel out. And I'm going to place my 2 moles of ammonia on top of the division line. Now, I want liters of ammonia. So I need to start working through my quantitative data on the ammonia side. And remember that 14.8 molar is the same as saying 14.8 moles per liter. And I can flip-flop that information over that division line. I can say 14.8 moles per liter or liter per 14.8 moles, right? I can flip-flop it however I need in order to get the unit I want and cancel the unit I want. So right now I've got moles of ammonia here. That means I need to have moles of ammonia underneath the division line. Remember that per is the same thing as a division line. So I'm going to put my liter on the top and I'll put my 14.8 moles of ammonia on the bottom. And that means that moles of ammonia divides by moles of ammonia, so it cancels out. And the only unit I've got left over is my liters. So I've managed to cancel out all of the units and arrive at the unit that I'm being asked for. I want volume, which means liters has to be on top. If I multiply everything that's on top of the division line, I multiply everything that's on the bottom of the division line, and then I divide those two numbers, I get 1.74 times 10 to the 3 liters. Another way you could express it if you wanted to, although most students probably would be content here, is you can just say 1.74 kiloliters. So that is a straight solution stoichiometry to solution stoichiometry problem. Another problem here, which is slightly more complex, well, maybe a little more than slightly more complex. We're kind of jumping the difficulty level for sure. They tell us a 123 milliliter sample of 1 molar solution NaCl is mixed with 72.5 milliliters of 2.71 molar solution AgNO3. Okay, so right there, right off the bat, before I even move forward, I'm going to write down what I have because I know that we've mixed 2 solutions together, so there's going to be a reaction. So I'm going to write my balanced chemical reaction for NaCl and AgNO3. So NaCl aqueous because it's in solution, reacts with AgNO3 aqueous because it's in solution. It's a double replacement reaction, so the silver and the sodium are going to switch spots and will produce sodium nitrate aqueous and silver chloride solid. To get these states of matter, you have to be writing states of matter. To get these states of matter, you're going to go to your solubility table and look to see. You'll see that when sodium attaches to nitrate, you get aqueous solution, high solubility. When silver attaches to chloride, you get a low solubility solution, solid. Now, the next thing I'm going to do, once I've written my balanced chemical reaction, is I'm going to write down, because they gave me quantitative data right away, so I'm going to write that down. NaCl, 123 milliliters, so 0.123 liters. Because I'm working with solutions, I'll generally want these in liters, so I just right away put it into liters. They tell me that it's 1.00 molar solution, so concentration is 1.00 molar. And then they tell me it's mixed with 72.5 milliliters, write that down, of AgNO3, 0.0725 liters of 2.71 molar solution. So concentration is 2.71 moles per liter. Now, next sentence, right? Right away, just with that one sentence, look how much info we've gotten, right? Now I'm going to see what else does the question tell me. What mass? Oh, mass. Okay, what mass of AgCl? I have to come underneath the AgCl. And I'm going to put mass is my unknown, is formed in the reaction. If I'm looking for mass of this, I have to put my molar mass. The question will never tell me to put it. I've got to put it. I have to know that. And so my molar mass of AgCl, I go to my periodic table. I sum the mass of Ag with Cl. I get 143.00 grams per mole. Now I look. What do I have here? Well, obviously I've got a stoichiometry question because I have an unknown in the chemical reaction and I've got a known. The interesting thing here is that not only do I have one set of knowns, I've got two set of knowns. And if you remember the last time we talked about stoichiometry, whenever we're given information for both of the reactants, this is a limiting and an excess reagent question. So first thing we do is we make a assumption. We say, well, what if sodium chloride is the limiting reagent? So what if the sodium chloride runs out? And as soon as this 1 molar solution runs out, I stop the reaction. How much solid, how much precipitate will I have produced? So I'm going to run my stoichiometry. Remember, and I'll put this in here just so that you guys remember, we're going to work through all of our quantitative data under the silver or the sodium chloride. Then once I've got moles of sodium chloride, I'm going to jump using the mole ratio to the silver chloride, and I'm going to work through my quantitative data on the silver chloride side until I get mass of silver chloride. Now I've got 0.123 liters. Let me move this up just so you can see this. 0.123 liters of sodium chloride. I'll put a check mark saying that I've used it. Now I need to cancel out that liter. So I'm going to use the only other piece of quantitative data I've got, my 1 molar solution. So I want to cancel out liters, which means I need to set this up as 1.00 moles. And again, I highly recommend you put moles of what? Moles of NaCl per, which is the same, divided by liters. My liters are on opposite sides of the division line, so they will cancel out. And now I've got moles of NaCl. Got nothing left underneath the NaCl. So now I'm going to use my mole ratio to jump to the unknown side, and I have moles of what I want on the top, moles of AgCl, moles of what I have on the bottom, moles of NaCl. You'll notice that the moles of sodium chloride are on opposite sides of the division line, so they divide by each other and cancel out. And then I'll use the only other piece of information under the AgCl in order to cancel my moles of AgCl out and be left with just grams. Multiply through and I get 17.6 grams. Now this is the theoretical amount. If all of this 0.123 liters of NaCl was completely consumed, nothing left over. There was 0 liters left over. All of that ran out. Theoretically speaking, I should produce 17.6 grams if I were to run this reaction in the lab. Now, it's not enough to just do this one reaction, this one analysis, because I also have to take into account, well, what happens if there's actually leftover sodium chloride? What happens if it's the AgNO3 that runs out? So I'm going to rerun my analysis, making the assumption that the AgNO3 runs out. Like I said, it's not the most eloquent, I guess, working through of this type of a problem, but it's quick, it's dirty, it gets you to the answer, and that's really what you need in the end. So I'm going to make my second assumption here. What if AgNO3 is limiting? So again, I'm going to work through all of my information. So I'm going to start with my liters. I'll go back up here and I'll cross out my liters. Make this smaller, maybe so you can see it all at once. There we go. The only other piece of quantitative data is my moles per liter. I want to get rid of this liter. So I'm going to put 2.71 moles per liter. I'm going to have that liter on the bottom so that it cancels with the liter from the volume. And this is moles of AgNO3. I've used up all my quantitative data, so now I have to use the mole ratio. And again, the ratio is 1:1, but I still have to show it. And I put moles of what I want, AgNO3 on the top, moles of what I have, moles of what I want, AgCl on the top. Oh, there we go. AgCl on the top, and then AgNO3 on the bottom, moles of what I have. You'll notice that the moles of AgNO3 are on opposite sides of the division line, so they'll cancel out. And then once I get over to this side, I'm going to use up my molar mass. I'll place my grams on the top and my moles on the bottom so that they cancel out with the moles of AgCl. Multiply through, and we get 28.1 grams. Now what I need to do is figure out, well, which one produced less. If NaCl runs out, if it's limiting, it produces 17.6 grams. If AgNO3 is limiting, it produces 28.1 grams. That means that the NaCl must run out first because it's limiting the amount of product that we're getting. So we're producing less product. We're producing 17.6 grams. Okay. So that's definitely a more challenging question because we're mixing gravimetric stoich with solution stoich. It's not just solution units to solution units. And then it's also challenging because it's a limiting excess reagent problem, but definitely something that you would definitely be expected to be able to do. Last example I've got for you is a solution to a gas stoichiometry problem. So the neat thing with all these stoichiometry problems is that even though we call it solution stoichiometry, call it gas stoichiometry, they really do mix between each other. And so if you see here, we've got an example of a student wanting to put 50.0 liters of hydrogen gas at STP. Now, right away, this here should be sending some alarm bells to me about gases, because the gas unit was the only time I saw STP. So they're telling me they want to put 50 liters of hydrogen gas into a plastic bag with excess aluminum metal. With a solution of sodium hydroxide that has a concentration of 3.00 moles per liter. Right away, before I even start anything, I am going to write my chemical reaction. So I have a student wants to produce hydrogen gas in a plastic bag reacting excess aluminum metal. So they're already telling me this is excess, so I already probably know I don't have to do any sort of limiting reagent problems. But I've got my sodium metal reacting with a solution of sodium hydroxide. There is there is water in here. You guys would not be expected to have water in here. I'm not 100% sure. Yeah, you guys wouldn't be expected to have the water in here. We would give you this reaction so that you knew what happened. So yeah, it says what mass of the NaOH is required if the reaction is as follows. They're giving us the reaction. This is a reaction you would not be expected to know. Now, I'm going to put the information down. So they're telling me 50 liters of hydrogen gas at STP. And hopefully I remember that at STP, 1 mole of any gas is equal to 22.4 liters. Remember, that's not given to you. If you didn't remember that, you would have your pressure and your temperature data at STP, and then you could use that in place. But I'm using the 22.4 liters. The other piece of information, they told me that the solution of sodium hydroxide was 3.00 molar. Okay. And they want me to know what volume of sodium hydroxide. So I'm going to put volume as my unknown. So if I look and I see I've got my classic stoichiometry set up. I've got information for one part of my reaction, and they're asking me for an unknown on the other part of my reaction. And I have to jump using my mole ratio. So, hang on, we're lagging here a little bit. There. So I'm going to start with, it has all the information. I'm going to start with the first piece of information. 50 liters of H2. I need to cancel out that 50 liters of H2. Well, I'm going to use my molar volume. And I want the 22.4 liters on the bottom of the division line so that the liter cancels with the liter. I'm going to put my 1 mole on the top, and that's of my H2 gas. Now, I'll make use of my mole ratio since I've run out of information here. And I'm going to jump over to